All right. So we're reviewing a couple kind of questions, broad concepts going into the exams Monday and Wednesday. The way that I'm setting these up for kind of big picture is I'm setting them up from um, pools of questions such that basically there's going to be enough different variations of the test that everybody's is going to be sort of unique, but it's still going to be covering the same concepts. It's just going to be covering different aspects of them. And so, in one sense, that's unfair. In another sense, that's completely fair because what it's trying to do is trying to discourage all of the clever mechanisms, secondary browsers, and all kinds of other stuff that students have used in order to try and get their way around some of these online tests. Um, it's trying to discourage some of those things, and what we're trying to focus on here really is we're trying to focus on what are the big principles and concepts. So atomic structures and interatomic bonding, you need to understand what those are. You need to understand how those are um, used in these. So there's going to be some questions about some different bond types. There's going to be questions about the structures of crystalline solids, because I think probably Dr. Wright really, I'd imagine, spent the better part of about 4 weeks really focused in on crystalline solids, if I were to guess. So there will be questions about crystalline solids. I'm trying to figure out how to incorporate those, because in this testing format, it's a little different than just handwriting these questions. It's a little bit different than having something handwritten and you can do the calculations by hand and turn those in. So I have to be mindful of the mechanism of turning in the test, and I have to format questions accordingly. So there's an awful lot of work that goes into the development of this. Crystalline solids and imperfections. You do need to understand defects and how those impact the structure of crystalline solids, because it's very important to know what kind of implications defects have in materials. It's really a thing that you've just got to understand. As soon as a defect turns into something like a crack, propagation becomes a huge issue. Materials sometimes in that case fail pretty catastrophically. So something you have to keep in mind for design. Imperfections, so that's diffusion, dislocation. Those are definitely going to be on there as well. Let me see what some of the mechanical properties are that you guys covered. Yeah, because you covered some of the mechanics of things like tension, torsion, compression, loading. Yeah, so you had a reminder on axial loading, knowing differences between stress and shear stress, strain, so lateral, tensile, and shear strain. Those are all things that you need to be able to kind of clearly identify what those are, why they're important. Torsion is a really big topic, so it's one that you need to know some things about. Linear elastic behavior, lots around what goes into making the stress strain curve what it is. Those are things that are also pretty important. So understanding what elastic deformation is versus inelastic. Yeah, so all of the information that you can pull out of a stress strain curve, what different regions are, understanding differences between resilience and toughness, and being able to read things like that off of graphs. All of those things are important. Understanding hardness in materials, what is hardenability, all of those sorts of things. So all of those mechanical properties are important. Let's see. Other topics. So we did 3, 4. 3, 4 looks like 5. So diffusion, I think diffusion gets cut. So we're not spending a whole lot of time on diffusion because that one's lower priority the way that we have this class set up. Diffusion, let's see. 7, 8, 9 are included. Yeah, so dislocations and strengthening mechanisms. So examples of how you guys did the working of materials, or how you talked about processes of materials, what kinds of things those processes do, especially in regard to how that changes or interacts with grain structure, kind of bringing all those concepts together. And then failure. Let's see, what stuff did you guys cover there? So understanding types of failure, structures of failure. All of these things are important to understand how and why something does what it does. Stress cracks and fractures, what it means to have a stress concentration, because it looks like you guys didn't spend tons of time. The fracture toughness. Okay. So you spent a little time with that, and you did talk about it in the context of the Sharpie testing lab. So none of these concepts are also like, none of these concepts are hugely unimportant. T on impact energy. Yeah, the effects of temperature on materials. What is creep? Like each of those are important concepts, because you need to understand what happens to a material under load. Yeah, then it gets into phase diagrams and some of the stuff we've covered. So the crazy thing is, in the last even less than a third of the class, we've had to cover approximately half the material, almost. It's a little bit silly. Yeah, 10, 11, 12. 12 we skip. 13, I think, also gets skipped. So I think it goes, yeah, 11, 17, 14, 15. So not having 16 in here really helps keep the confusion or the unnecessary confusion at bay. So So you do need to know a couple things about ceramics. You do need to know, you need to really understand the phase diagrams and phase transitions. Understanding what some of these other mechanisms are. So I would say it's probably going to be a third or less on like crystallinity type things. And it's going to be much heavier on sort of all of the other things, especially in terms of phase diagrams and things, because it's, yes, it's important to know what a material's crystalline structure is. It's more important in most regards to put it into an end application to understand the mechanics of how that atomic and molecular level structure translates to real world properties. That's the best way that I can think of to phrase that. Because you need to understand that there's a difference between BCC and FCC, but that's going to be very much less important for the end application than some of the macro scale properties that those principles create. And because we didn't get all the way into composites, that really simplifies things down. So really, you only have to understand mostly qualitative properties about polymers, and fundamentals of crystalline structures and behaviors and mechanics of ceramics and metals. That feels like a ton of material, but it's also actually not, because there's a lot more depth that this could have than one semester allows. Let's see, other questions. So in those, there are calculations involved with all of those, but there are going to be a lot of qualitative questions that are, the answers are going to be set up in such a way as to cause you to think about these things. Equally, because you guys have some time constraints, especially in the Wednesday class, I can't design it to be like a 6-hour brain buster exam, as much as that's kind of what's needed for this class to close it out. So yeah, there's a handful of chapters where there's a lot of calculations, and like, because you're going to have the equation sheets, I don't know if it's going to be as good a use of time to spend lots of time doing lots and lots of the calculations outside of things like the phase diagrams, and phase transformation stuff, where people are still kind of a little bit weak. So you really, really, really want to go back and do extra problems in those areas, so that you can have a good showing on the exam, because I need to evaluate those things, so you know those are coming. So this is going to be one of those tests where I could just about give you the questions ahead of time, and probably the results are still going to be what they're going to be. Because I don't have all of them, I haven't thought of exactly what I'm asking in terms of the crystalline bonding and some of those things. All right, other questions. I know there's a couple of you that are having different internet issues and you're jumping in and out. Surely there are other questions from at least a few of the concepts that you guys are feeling maybe a little bit weaker in, going into the final. Because the polymers and the processing, that probably is going to be more straightforward. Their behavior is very much different to that of the metals, but we've talked about that, I think, pretty thoroughly. So I haven't spent a lot of lecture time trying to do things like come up with Kahoots games and stuff, because I wanted to make sure we had a chance to actually get through the material, which is the important part, so that you guys would have time to absorb it and process it before being tested on it. Otherwise, we run out of time. I can take a closer look at the phase diagrams. So let me pull back up. I think that is 11, I think, is really where kind of the good stuff is. Yeah, so this is kind of some 910 review material. Let's do this. Kind of broadly, the phase diagram has a few different regions. So some of you, for instance, were using probably something like a quick Google search or chat or whatever answer for the compositions. What we went over here for the slides was a little bit different range. So this gave up to about 1.4 weight percent for the range of steels, and then cast irons were anything above 3. So the normal steels were up to about 1.4. High strength steels are basically the things that are in between these. And you start getting over about 3, you start getting into cast irons. So something over about 1.4 to about 3% is the high strength steel region before we get into cast iron. So there was some frustration around that. That was one of the questions that got thrown out from the last one, because like everybody did poorly on that. So specific regions of these phase diagrams mean different sorts of things. When we talk about a specific temperature, the way that you evaluate this is by doing something like bringing it into PowerPoint or similar software. And so one of the examples would be something like, if I were to take a line across at, like, say 1300. So that's going to be somewhere here in between. I'm going to make that a level line. I'm going to bring this down slightly so that it's about at the halfway point here. So about halfway through, I'm going to make sure it's coming all the way across. What I can then do is add another tie line here from 1300 down. And I want to make sure that it's straight and it's not like jaggedy and doing weird nonsense. Some of you did something like this and then said, oh, the answer would be 1.3 and 2.9 or 3, and then called it done. You haven't really started the analysis yet when this is the case. So you've got your tie line. Your starting point is this 1300, you're trying to look at composition. This phase envelope, meaning whatever is enclosed by this region, right? Above the eutectic, you have some liquid, period, always, right? So just saying the composition over here is alpha and carbide or something, you're completely in the wrong region. You're in the wrong phase envelope. Very, very far from correct. So in this region, you can only have gamma, so austenite, and liquid. That's it. There is nothing else in this phase envelope. Just like inside here, there is only austenite. Over here, there is no liquid inside this phase envelope. So this is cementite and austenite. That's it. To get below where you start recrystallizing from austenite back to alpha or ferrite, you have to get below 727, period, the end. So a lot of the heat treatment questions were highlighting specifically these temperatures are specific for a specific region. So they're very key. In order to reach liquid, you have to be above 1148. Above 1148, for sure, you have liquid in your composition, period. If it's exactly eutectic composition, which is typical cast iron, because of its lowest melting point at the eutectic composition, 4.3 weight% carbon, at that point, you only have liquid above 148. There is nothing else because you're in the phase envelope that is only liquid, right? Ferrite only is just this very narrow little sliver of a region. So unless you have virtually pure iron, you're almost never even going to see this region at all. The zone is there, but that's why it's very hard to analyze things like inside this alpha plus gamma window. So this is only austenite and ferrite. As you continue to cool down, you're going to end up with only ferrite and some amount of cementite, probably in the form of some kind of perlite with a lot of the concentrations that we're using. So above this, you start getting some different phases. But this is the important thing to understand about how to read off of these phase diagrams and understand, okay, so now I have down here, I have my effective concentrations. If I started from something like a 2 weight%, you can change the color on this one and you can say, all right, my black line is going to be from 2% and it's going to be straight up. The trouble with something like PowerPoint is you have to dissociate it from all the other gibberish here. So right about here is roughly straight up and down. So if we use a black line there, we can see a little bit more clearly the difference between 2 and 1.2, 1.3 is probably 1.25 here, versus 2.9 or 2. Yeah, I'd probably say about 2.9 there. The difference here to here and the difference here to here give you that R and S value that's used in the calculations for chapter 10. So we don't go back over those, but it's important to understand those. It's also important to be able to identify on these cooling curves what these things are and what's going to be formed as a result of those, right? So any combination of questions I could derive from this graph that are conceptual and that meaningfully test your knowledge in a way that other websites and Googling and stuff is just going to waste your time, right? So Really understanding hardenability, especially because we had a lab on it, and some of these concepts you guys had just missed. A lot of the particulars of heat treatment and the mechanics of some of the hardening and what's actually going on. Different types of annealing. There's a lot of different things that I could identify there. There could be a lot of questions about phase diagrams and other things as well. So those are important. So there's probably going to be a number of graphs that are involved. But I'll try and make sure that they are like in the example with this one where I'm drawing in all of these tie lines and things. If you guys did the calculation and the actual answer was, we'll just say like the composition of air, right? Roughly, it was 19% on one side and 21% on one side and 79 on the other, right? So roughly like the air composition or something. If that was the correct answer and your answer was 15 and 85, you still got the vast majority of the credit for that question. If you put down 1.2 and 2.8, you did not get most of the credit because you did not even attempt most of the work as evidenced by your answer. So it was clear that that was not a concept that you fully grasped. So you'll want to review that calculation method and pay real careful attention to the order of things like the R and the S, which side is which, all of those sorts of things. Because if you're looking for the weight fraction of one thing, you calculate it very differently than you do for the other. So R over R plus S versus S over R plus S is the answer to two completely different questions, and you need to really pay attention to what you're looking for, what you're calculating. And then some of you came up with like a 350% composition or something, which was very impressive, although utterly non-physical. So that was pretty interesting. So another good one to think about, I imagine you guys didn't spend tons and tons of time in the polar coordinate space. Let's see. And I don't have the majority of those slides, so let me jump back in here. Here's some of them. Let me see what kind of time we've technically got left, because it's probably not much. A little bit. Okay, so just a little bit. So let's go ahead and go through a couple of these concepts. I think that's where probably, if a lot of students were honest, that's one of the areas that they struggle the most on the whole. So yeah, why not have to completely reteach this whole section? Atomic packing factor, trying to get you a number of approximate efficiency of atomic packing. So these are important concepts to know about. The volume of the atom being just volume of a sphere, so things that you should know. The R changes and the A changes based on whatever the length of a unit cell is. And that A changes for a number of different types of atoms and all those sorts of things. So the radius becomes pretty important. So atomic packing factor is a good one to know. For BCC, it's a little less straightforward. So again, some of those sorts of things are going to be given. Face-centered cubic, again, has kind of its own because of numbers and because of geometries and things. So the FCC stacking becomes a little bit more efficient in a lot of ways. Hexagonal is where stuff really starts going strangely. And I think there's an example of a calculation done for a couple of these. So let me jump over to the slideshow. What this will do is give a sense of about the way that density works for these. So it has to do with number of atoms. So theoretical density, those are fun. But I think it's in this chapter where they start talking about, so it is important to understand anisotropy versus isotropy. So if they're random, they're isotropic. Those are things that are important to understand. Yeah, so point coordinate. So this is where a lot of confusion can come in. A point coordinate is showing you from the origin where is the corner of this unit cell and how far away is it. So all it is a vector. So, and I know you guys hate it when instructors say, well, all it is, but it's a coordinate in three-dimensional space. So 1, 1, 1 is one unit in each of these axes. So it's trying to give us a vector direction basically for what the point is actually doing in space. So there's a stepwise process that you need to go through in order to calculate these. So this is why I wanted to go ahead and start the slideshow instead of just talk about it at the end state. Vector has a tail and a head. Where it's going on the unit cell is dependent on how it's working in 3D space. Think back to the stuff that you guys have done in SolidWorks, right? You have to go from one coordinate to some other coordinate in order to get those specific dimensions. And where you take that measurement from changes how that works. Then the computer does all sorts of stuff in the background, turns it into an STL, which is a bazillion different triangles. And what it's doing is it's turning some of those coordinates into vectors from a given point, so that it can map a surface out with reasonable precision. So you start by looking at the vector tail. Then you look at the vector head. So the tail, in this case, is at 0, 0, 0. Doesn't have to be, just happens to be in this case. Then at the, you determine where the head is, which is 1, so a full unit in the X, half a unit in the Z, and 0 in the Y, right? So They use A, B, and C often as designators. So A, 0 in Y, and half of C for where the head goes. You take the difference between those coordinates and you get 1, 0, half. And so you can also do this one very quickly by inspection and determine it's 1, 0, half. But this is the formula. So at this point in the semester, rather than try and reinforce the why and the philosophy behind it, I'll tell you the pizza dough analogy. This is one of the concepts where we're going to stretch you like pizza dough beyond what you actually have to be in order to fit the engineering pizza box. And when you relax sometime after the fact, more of this will make more sense. But in the middle of it, a lot of this is kind of confusing. Just focus on understanding how to use the formula to find the difference for these crystallographic directions. X2 minus X1 divided by the length of a unit cell on that side. Y2 minus Y1 divided by the length of a unit cell on that side. Z2 minus Z1, this is just a simple difference formula. This is not rocket science. And then you reduce them to integer values, because for any of these indices, we need to have integer values for things. And those indices, 2, 0, 1, are a result of taking this 1 half, or 1, 0, half, and multiplying everything by 2, right? So the indices for this one are pretty straightforward. So another example, if it starts out halfway, it's the same thing, except in this case, you have the starting point at A, half, 0. So here, the position 2 is minus A, B, because it's all one full unit, B, and then C, because it's one full unit, out. Otherwise, it might be 0 and come back over here, do other kinds of weird stuff. Minus A is the end point minus the origin point, which was a positive A, over A, is equivalent to minus 2. So we should be able to see that it goes backward 2 into the plane. So that makes sense. B minus half B over B gives us half. C minus 0, because it starts off at 0 for Z. C minus 0 over C gives us 1. So we multiply through for the integers, and we get minus 4, 1, and 2. And so we get 4 bar, 1, and 2 is the notation for the negatives. So these indices are really not actually all that bad, but understand that there are basically variations of all of these, and we always indicate them with the angle brackets. So when things are skewed for these crystallographic directions and they give us a value for A, we know what the unit cells are. We determine, we know what we want to know what the linear density is in the 1, 1, 0 direction. So starting from our ending point, we can get our value. So in this case, we've got a fairly simple example. A is 0.405 nanometers, but 2 divided by the root 2 is from our original formula many slides ago, that we can use these. The planes is another one where a lot of students get super duper hung up. And that's where we'll spend probably the rest of this, because that's probably one of the biggest points of confusion. So you have a specific algorithm, and you need to be thinking in terms of, if I see this problem, do these steps. Don't ask questions about those steps. Just tell your brain to shut up and walk through the steps. It's really the best way I can think of to tell you how to deal with these. Rather than trying to philosophically understand why these things are what they are. They wrote out the steps for you clearly, plainly. Write them down, follow them. If a plane passes through a specific origin, establish a new origin of another unit cell. So I think they give us an example of one of those. You look at the values of the intercepts of the plane with the XYZ axes. Then you take the reciprocals of the intercepts. Because it is an intercept, you need the reciprocal to be going the opposite direction and get along what was the original plane in order to identify what the Miller indices are. Why? Because trigonometry. It's a thing. Think about planes, think about the principles of reciprocals and doing the opposite of that plane in order to identify what these things are. So you take the reciprocals, you normalize them, meaning you do a similar kind of thing to what we were just doing with turning them into integers, and we'll see what those look like. So A, B, and C lattice parameters are going to be helpful. And then enclose the resulting Miller indices in parentheses. No commas or anything like that. So for this example of a plane, this is one running through diagonally, but it's forming a line only really in 2 dimensions. So there's really only 2 that are changing. So you don't need to relocate through a different origin because it's not passing through the origin. So a lot of times step 1 technically gets skipped. The intercepts. So the plane crosses at A. It crosses everywhere in C. So it's a line in the plane of that would be C along an XY plane at any C. It's an infinite number because it's a line. Why? Just trust me, I'm a doctor. B is the other intercept on the y-axis. So there is no actual intercept for C, meaning when we take the reciprocals, we get 1 over A, 1 over B, and 1 over C. So we normalize those by multiplying each of them by the actual unit cell length, and we get 1, 1, 0. Because we have 1 in A, 1 in B, and 0 in C, it doesn't cross ever in C. So anytime it's not crossing a third axis, one of the values is going to be 0. So we don't have to do the reduction step, and 1, 1, 0 becomes our plane. Here, different case of parallelism. ZY plane, it does have an intercept for A, and this one's going to be a little bit different. So we're not relocating because it doesn't go through the origin. The intercepts in 2 of these axes are going to be infinite because they are parallel. So it actually forms lines effectively across 2 different planes within our axes. We do the reciprocals. So we get 2 over A, 1 over basically B over infinity, C over infinity, multiply through by those unit cell directions, and we get 2, 0, 0, which should make sense because we would look at this plane and go, oh yeah, well, this plane should be 1/2, and then 0, 0 because it doesn't cross those. So 1/2, 0, 0 converted up would be 2, 0, 0 because of the way that these are reciprocated, because they are perpendicular to these lines that we're working through. The reduction, again, we don't have to do any further reduction, and we get 2, 0, 0 as the Miller indices. Here, where we're crossing all three, so we're crossing at 1/2, 1, and maybe 3/4. I think that's, yeah, I think that one's set to be 3/4. So 1/2, 1, 3/4. Multiply through by those, or take the reciprocals first. So then multiply through by those indices, or multiply through by those unit cell lengths. All of those cancel out to leave us 1, 2, 1, and 4/3. So we have to multiply by 3 to get rid of our denominator. So we get 6, 3, and 4 as our Miller indices. So these are telling us something about the angle of tilt in three-dimensional space relative to the origin, about what these planes are doing. So they are the things that are crystallographically equivalent, are these. So there's a whole group, 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 1, 0, 0. So basically those three and the opposites of those three, meaning if any of them is planar in two of the axes, it is in the same family as one that is planar in any two of the other axes from any different side of the origin, is really all that that's saying. So up here in this example, a couple more. Yeah, so we don't have another example. We have it here. So the family of directions, crystallographically equivalent here, in terms of the coordinates are similar. So any of these vectors that are in a that are constrained to a single plane and are not across two different planes and are not therefore really two-dimensional, they're effectively all the different one-dimensional indices are in the same family as the other ones that are similarly constructed. So there are a lot of different kinds. So 110 is a common crystallographic plane for a lot of glasses. Naturally, there are also some examples of some 111s. The difference is trying to take it back to a macro scale so that you can have a sense of what that means. Is 111 is a sharp diagonal. So let me see if I can find a quick example of what that looks like. The way that those materials tend to fracture, for instance. Let me see if I can get you an image. Does anybody have this info. You can kind of see it. Man, I can't be the only one in the entire stupid universe that knows this. Yeah, here we go. This will be about as close as I can get you to understanding why this is actually important. Silicon wafers are very highly ordered crystalline structures for a specific reason. Here are the differences between a 100 orientation, a 111 or a 110 orientation, and a 111 orientation for the Miller indices. It's used to determine where and how to cut the crystals because they will fracture very differently. So this is a quick way to tell. 111 is always going to fracture triangularly. 100 is always going to fracture along planar lines. Always. It's like you might get a couple that are because of defects in the material or something. You might get a couple that will give you kind of a slight, it'll still give you kind of a straight edge, but it'll be kind of an off angle rectangle or something. It's still not going to be primarily triangular. So 111 fractures into these really sharp shards. 110 and 100 do not to the same degree. So 110 is a little different. I wish they'd have shown an example. I've primarily seen 110 and 111 wafers in use for different cases, but those are things that are key, and this is why that is important. Because those Miller indices tell us something about what the bulk behavior is going to be like. So these are going to be, yeah, the 111 I think is going to be planar. The 110 is going to be always at like a 45 or so. So I think that one maybe fractures into much different shapes. They often are more like trapezoidal looking almost. And then 111 is really sharp shards, the way that the crystalline lattices break. So they shear along those planes, and that's how material failure propagates. So it's tracking based on the arrangement of the atoms. How is it going to break under different stress conditions? So hopefully that makes a little bit more sense. But I know that's an area where there can be lots of confusion. All right. Any final questions? So we only got a couple more minutes. All right. Well, if not, hopefully everyone has a good time studying and cramming and or learning for the first time this semester before the test. And I will see you guys next week.